and we can identify the bolt that carries the largest load and ensure its safety. And when the bolt is bearing transverse load or torque, we consider this under two conditions for the ordinary bolt joint or the Raymond bolt joint. We can use the equation of Raymond bolt joint to calculate force distribution for ordinary bolt joint. But when we calculate the preload, we should use the equation of ordinary bolt joint. Because for Raymond bolt joint, it uses shear strength to resist the external force. But for ordinary bolt, it uses frictional force to resist the external load. And then, according to force analysis, we know external loads acting on bolt, and each individual bolt carries either tension loads or shear loads or variable force. To prevent bolt failure, we should choose proper size of bolt. Then we use strength calculation to obtain the proper size of the bolt. And it should satisfy the strength criteria. Under different conditions, we use different strength criteria. This is for loose bolt joint, and this is for bolt just carries preload, and this is for the bolt is subject to preload and axial force, and this is for the bolt subject to preload and variable force. And this is bolt bearing tensile stress. If the bolt is bearing shear stress, we use this to calculate the size of D0. And then we learn the design of bolted joint. We should do structure design first, and then do force and strength analysis. And this is the property classes for bolt. And the numerator before the decimal point is the tensile stress divided by 100, and the numerator following the decimal point is 10 times the ratio of yield stress to tensile stress. And so from the property class, we can know the tensile stress and the yield stress. And this is the design procedure for bolt. First, decide the pattern of bolt layout and the numbers of bolts, and then analysis operating load on the bolt joint, and then determine the load each bolt subject to according to the bolt joint type, and then determine the critical section dimension, usually the minor diameter D1. And we can use the strength analysis, and then decide the size of bolt, large washer, and so on. And this is the example in your example. Let me see. On page 81 in your textbook. We have learned it last class. And is another example for a cast iron bracket. Okay, let's see. Look at this example. A cast iron bracket is bolted to a steel foundation. The bearing is supposed to carry a load of P. Below the value of P. And then the angle between the force and the horizontal line is alpha. Alpha is 30 degrees. Then determine dimensions. Detailed dimensions are shown in this figure. And then we should determine the maximum axial force on the bolt and check the connection. So first, we do the structure design and identify the numbers of bolts. From the structure below 1, 2, 3, 4, 4 identical bolts are needed, and it should be preload. And then we do force analysis. Force analysis simplify the external force P. Then we resolve load P into vertical and horizontal components. The vertical component is the axial force, and the horizontal component is shear force. And we can calculate the axial force and the shear force. For axial force, it's the load P times sine alpha. Alpha is 30 degrees, and shear force Px is P times cosine alpha. And then the shear force or the horizontal force may cause overturning moment. And then we can calculate the overturning moment use the force times the distance between the force and the centroid. And then determine the force on each individual bolt under the axial force. There are 4 bolts, so the distribution on each bolt is the total axial force divided by the number of the bolts. So it's 5,000 divided by 4. There are 4 bolts. And then compute the force on the bolt to resist the not bending moment, the upsetting to resist the upsetting moment M. We use these equations from force analysis, and we calculate the maximum force to resist the upsetting moment, and the total actual force on the left bolt is the Fa plus F max. Fa is the distribution of total actual force on each bolt, and F max is the maximum force of the bolt to resist the upsetting moment, and then to resist actual load, we have this. Then frictional force should larger than the should larger than the transverse force Px, and this is the factor, and then we can calculate the preload should larger than this, and then consider the left bolt, which is subject to the maximum force. We have this. The bolt. The actual force on the left bolt. We use strength analysis to calculate. This is the preload, and this is the F, the maximum actual force distribution on the left bolt. So we calculate the actual force acting on the left bolt, and then we check the connection to prevent crashing, and we have these equations, and the effective error A and effective section modulus we obtain from this table for this shape, and we can calculate A and W. And to prevent leakage of the left bolt, we have this equation, and then calculate the design is acceptable. So this is for example 7. And for the exercise, we know the bolt type is ordinary bolt joint, and we know the anti-skate factor and the coefficient of friction and the allowable stress. So then we need to design the bolt diameter. There are two bolts, and first we do force analysis, simplify the load, and there is a transverse force and a torque, and then determine the forces on each individual bolt under transverse force is the total transverse force divided by the number of bolts, and then compute the force on the the maximum force on the bolt to resist the torque. We use this equation from force analysis, and then determine the bolt. Find the bolt which carries the maximum force. It's the left bolt. Okay, and then determine the preload, and then we use strength analysis to determine the diameter. The calculated strength on the left bolt should less than the allowable stress. And then we calculate D1. The D1 should larger than that. And for all the bolts, the D1 is standard. We then from this table we can choose this bolt. For this bolt, the diameter D1 is larger than the calculated value. So we choose M18 bolt. 18 means the major diameter, and this is the minor diameter. So this is measures to improve the strength of bolt joint, and we should first decrease the variation rate of bolt's total tensile load. The variation rate of axial service load F varies from 0 to F, and then the variation rate of total tensile load is varies from F0. F0 is a preload to preload plus this. F is the maximum external force. Then we can decrease CB or increase CM to decrease the strength. Then the first measure is to decrease the stiffness of bolt. For example, if we decrease the stiffness of bolt, means to decrease the CB. The CB prime is less than the CB, and then the we can know this, the delta F prime is less than the delta F. Delta F prime is for the decreased stiff bolt. And the second measure, we can use this, increase the stiffness of the members or the joiner. For increase the stiffness of CM, the delta F prime is also less than the delta F. Or we can use comprehensive measures increase the stiffness of bolt and decrease the stiffness of bolt and increase the stiffness of the members to decrease the delta F. And then two measures should be used. We have to use flexible construction. For example, to add elastic components. And to adopt metal thin washer if there is any, or adopting O-type joint ring. And to decrease strength concentration, first infinite reduce or cut unloading slot like this to avoid or reduce additive stress. We should to adopt measures considering structure, manufacture, and assembling precision and to prevent distortion or to prevent uneven at the surface, or we can adopt dummy club or other elements. And this is to avoid special process and we can use forging. Or another manufacturer to improve the vertical intensity. And all of this is for screw joint. And for screw drive, it's for the screw drive, the types of screw drive according to the purpose. It includes transferring power screw, transferring moment screw, and adjusting screw. The transferring power screw is to transfer power, and the transferring moment screw is to transfer moment, and adjust screw is to adjust the relative position of bolt and members. And according to friction character, it includes gliding screw, rolling screw, or static pressure screw. For example, these are adjusting screw to adjust the position, and this is the transforming moment screw for a fade machine. And for jack and forging press, this is transforming power screw. And in a saw machine, this is an adjusting screw. For vise, this is an adjusting screw. And also for micrometer, this is an adjusting screw. And this is the structure of large for the screw drive. And this is the material of slide screw. And this is the design calculation of slide screw. And this you just need a basic understanding on this. So this is all about the screw joint and screw drive, and you should focus on the screw joints, and you should know the types of screw of both joints, and you should master the strength and force analysis of for the bolt and the bolt group. And now let's proceed to the next chapter, the belt drives. Mechanical drives are usually used to transmit power and motion from one rotational element to another, including belt drives, chain drives, gear drives, and so on. In this chapter, we'll discuss in detail the features as well as analysis and design of belt drives. There are 4 goals for this chapter: to master the characteristics of belt drives and the working condition analysis and power transmission capacities, and then do design of belt drives. And belt drive is one of the major types of flexible drive. Belt drives are usually used when the certain distance between rotation shafts is large. In a power transmission system, belt drives are usually used at the first stage or high-speed stage for the power source. For example, in this figure, belt drive is used between electric motor and gear reducer to transmit power and motion. So it is usually used at the first stage or the high-speed stage for belt drive. And a typical belt drive consists of a driving pulley and a driving pulley and a continuous belt. And the driving pulley is smaller usually, and the driving pulley is larger. When a belt drive is used for speed reduction, the small driving pulley is mounted on the high-speed shaft, while the large driving pulley is connected to the driving machine shaft. And there are 2 typical layouts of belt drives: the open belt drive and the closed belt drive. An open belt drive is used when the driven pulley is to be rotated in the same direction as the driving pulley. And for the cross belt drive, the driven pulley rotates in the opposite direction to the driving pulley. There are two typical layouts of belt drives. And belt drives include frictional and machine belt drives. There are four types of frictional belt, that is flat, V, rippled, and round belts. This is the sketch figure of the cross section of various belts. A is flat belt, B is V belt, C is rippled belt, D is round belt, and E is for the machine belt. Flat belt, like this, are the simplest and least expensive type, with narrow rectangular cross section like this. This is for the flat belt. The contact surface between the belt and the pulley is the working surface. That is the working surface of flat belt. And the driving force is limited by frictional force between the surface. And flat belts are usually used at high speed and relatively low powers. And for the V belt, it has horizontal cross section and the two contact siders are working surface. There and there are the working surface. The friction on V belt drivers is larger than that of flat belt. So V belt has higher pulling capacity. When high powers are to be transmitted, we usually choose V belt. And a rippled belt combines a flat belt with V belt. The flat belt section carries loads, while the V belt section provides grip on the sieve. And wheels with a flat profile are called pulleys, while wheels with grooves are termed sieves. And this is the fingers of rippled belt. And the rippled belt can improve load carry capacity and avoid high bending stresses. Round belt have circular cross section and are limited to light duties. machine belt engages with mating tools, wheels, and universally used for synchronized power transmission to ensure that the driving sheave always rotates at a constant speed ratio to a driving sheave. The power transmission capacity of a machine belt is limited by the tensile stress of belt and the shear stress of corks. And it possesses high-speed characteristics of flat belt with power capacity approaching that of chains. And this is the types of belt. And among these belt types, V-belt have the widest industrial applications, and this figure shows typical cross sections of a V-belt and sheave groove. The pitch line, which is designated as N, the pitch line, is the neutral axis of the belt section, and the wings of pitch line, or the pitch wings, BP, keeps constant as the belt bends around sheaves. And the groove wings, BD is measured at points where the neutral axis of belt contacts the groove. This is the BD. And the datum diameter DD, that is the DD, is measured at the groove wings BD. And pitch diameter DP is measured at pitch wings BP. We have DD is equal to DP. And the sheave diameter D. Sheave diameter D is at the point where the neutral axis of the belt contacts the sheave groove. So we have dP is equal to dd is equal to sheave diameter d. At pitch diameter or sheave diameter, the belt and sheave have identical linear speeds. And the wedge angle phi for V-belt, phi is 40 degree, and groove angle phi 1. Phi 1 varies from 32 degree to 38 degree, and the design will increase friction and transmitting high torque for V-belt. and that the red line represents the pitch line. The pitch line. And when the belt bends around shifts, the width of pitch line BP keeps constant, and the surface through the pitch line is called pitch surface. Pitch surface. And when the belt bends around the shifts, the surface above the pitch surface is subject to tensile stress, and below pitch surface is subject to compressive stress. So let's have a rest, okay?
OK，老师。
Okay, have a rest. Okay, let's continue. And we know the dimensions of we built. And we built have two types, that is standard we built and narrow we built. And standard we built are designated by letter Y, J, A, B, C, D, E, with an increased area of cross section. And for narrow we built, it has greater height at the same pitch with BP and are labeled SPZ, SPA, SPB, and SPC for different cross-section size. And for standard we built, the wedge angle phi is 40 degrees, and the ratio of H to BD is 0.7. And for narrow we built, the wedge angle is also 40 degrees, and the ratio of H to BD is larger than that of standard we built, is 0.9. And this figure shows the construction of typical we built. The outer fabric cover gives good durability, and the high strength cores increase tensile stress. The rubber provides flexibility for the we built. And this table lists parameters of cross section of standard we built. For type Y, the B is 6, B, and BD is 5.3, H is 4. Then the error A is 18, and from this table we can find that from Y to F, the error of cross section increase. Remember, this is the cross section of Y. This is for Z, A, B, C, D, E, F. From Y to F, the cross section will increase. And this is geometrical relationships in belt drivers. This angle is theta. And then the contact angle for driving pulley. For driving pulley, the contact angle is alpha 2. And for driving pulley, the contact angle is alpha 1. And this angle is theta 2. And we have 4 driving pulley. For driving pulley, the contact angle alpha is pi minus 2 theta. And for driving pulley, the contact angle alpha 2 is pi plus 2 theta. And this angle is equal to the angle theta. So this is theta. And if theta is small, we have this. Theta is approximately equal to sine theta. And sine theta is determined by this length divided by this length. And this length is the distance between the centers of the two pulleys. And this length is the difference between the diameter of driven pulley and driving pulley. So we have this. The sine theta is determined by this length divided by this length. And this length is the R of the driven pulley minus the R of driving pulley. So it's d2, half of the d2 minus d1, and then divided by the distance A. It's sine theta. When theta is small, sine theta is approximately equal to the value of theta. And then we have this. We calculate the contact angle is pi plus or minus dd2 minus dd1 divided by distance A. We can calculate the contact angle of alpha 2 and alpha 1. For alpha 1, there is minus. For alpha 2, there is plus. And then we can calculate the value of alpha is 180 degree plus or minus dd2 minus dd1 divided by 8, then times 57.3 degree to calculate alpha, contact angle alpha 2 and alpha 1. And the belt length, the total belt length is the length of AB plus the length of arc BC plus CD and plus the length of arc DA. And the length of AB is equal to length of CD. So the total belt length L is 2 times length of AB plus the length of arc BC and plus the length of arc AD. And then we can calculate the length of a belt. It's approximately equal to this. A is the distance, and D2 and One is the diameter for driven and driving police. And then we can calculate the center distance A from this equation because DD2, DD1, and the belt length are standard. We can choose standard values for DD2, DD1, and belt length. And this table lists the value of length LD, and this is for the type of V belt, Y type, Z type, A type, B type, or C type. And when the sieve or pony diameter is specified as datum diameter DD, the belt length is termed datum length LD. And KL is correction factor for belt length. And these are examples of belt drive applications. Now, let's proceed to the fourth analysis of belt drive. The belt clamps firmly against the pulley surface with an initial tension F0. It ensures the belt works properly under design load. And without load operation, the tensile force on the belt is F0. So we have F1 on this side is equal to F2 is equal to F0. And in node operation, the driving pulley and the driven pulley rotate in clockwise direction, and the bottom strand of belt is tight side. The upper strand of belt is slack side. The driving pulley applies frictional force in clockwise direction, and the driven pulley applies frictional force in anti-clockwise direction. The tensile force in the bottom strand of belt increases from initial tension F0 to tight tension F1, where tensile force in the upper strand drops from F0 to a smaller value of F2. It has this. So the tensile force F1 is not equal to F2. Assume the total length of belt keeps constant. Therefore, the increase of belt length in tight side is the same as the decrease of belt length in the slack side. So we have F1 minus F0 is equal to F0 minus F2. Then we can calculate the F0 is half of F1 plus F2. And the total torque should be 0. Should be 0. And we can calculate the tight tension and the slack tension F1 and F2. The FE is effective tension on the belt drive. FE is determined as F1 minus F2, and FE means the circumferential force transmitted by belt. And the power transmission capacity P of a belt is the FE. FE is the force transmitted by belt. It's F1 minus F2. FE times the speed V and divided by Y1000. Therefore, in order to ensure belt to transmit power P at speed V, an effective tension FE must be guaranteed between the belt and the pulley. In other words, a minimal initial tension must be maintained on the belt. And FE is the force transmitted by belt. P is the power transmitted by belt. And when there is a slip change between belt and pulley, the friction reaches the maximum and the effective tension FE reaches the maximum. So we can calculate the maximum effective tension FEC. And consider a differential belt element shown in this figure. Its belt is subject to a normal force dN, and a frictional force along the contact arc FDN, and the direction of the frictional force is vertical up. And the tensions for belt, for the upper belt, the tension for the upper there, the tension is F, and for for the so there the tension is F plus DF plus DF. First, the tension in this direction is larger the tension in this direction. And from force equilibrium conditions, we have the total force on the horizontal direction is 0, and the horizontal direction, the total force is 0. So we have Dn is equal to the horizontal component of F and the horizontal component of F plus dF. So we have dN is equal to F times sine half of d theta and plus F plus dF times sine half of d theta. We have this equilibrium condition. And in the vertical direction, we also have this. The total force is 0. So the frictional force, the direction of frictional force is vertical up. It's equal to the vertical component of this tension minus vertical component of this tension force. So we have this. F times dN is equal to F plus dF times cosine half of d theta and minus F times cosine half d theta. F is the coefficient of friction between the belt and the pulley. Alpha is contact angle, and E is the basis of the natural logarithm. And then we can have this. F1 divided by F2 is equal to this. And we know that the maximum effective tension FEC is equal to F1 minus F2, and then we can obtain this. And FEC is the maximum effective tension, means the maximum force transmitted by belt. And and these are factors influence the maximum effective tension FEC, the initial tension F0, the contact angle alpha, and the coefficient of friction F. And if the initial tension F0 increase, then the maximum effective tension FEC will increase too. But if the initial tension is too large, it will reduce belt vertical life. If F0 is too small, so the belt is easy to slip. So should choose proper value of F0. And for the contact angle, if the contact angle increase and the total frictional force will increase, and then the maximum effective tension will increase too. And then it can increase the power carry capacity of the belt drive. Also, if we increase the coefficient of friction F, then the maximum effective tension FEC will increase 2. So these are the 3 factors influence the maximum effective tension. And then let's do the stress analysis for the belt. Okay, then well, the force analysis is used to calculate the force transmitted by belt, and usually we only consider the tensile stress on the belt. When we do stress analysis, we know that the belt is subject to tensile stress, bending stress, and other stress. For tensile stress, we have for the tight side, the tensile stress is the F1. F1 is the tensile stress on tight side divided by the cross-section area. And for slick side, sigma 2 is F2 divided by the cross-section area. And for the centrifugal stress, acting on the belt creates centrifugal tension Fc, and we also can calculate the centrifugal stress sigma C. Sigma C is this. Use this to calculate. And for bending stress, we also can calculate sigma B. Use this equation, and H is the belt height, and D is the sheave diameter. E is the modulus of elasticity. And then we can obtain the stress distributions. Is this means for the centrifugal stress, and this is the centrifugal stress, and this is the tensile stress. It's for the tight side, the tensile stress is large, and for the slick side, the tensile stress is small. And this is for the bending stress. We know that bending stress can use this to calculate. And D is the sheave diameter. So for the driving pulley or the driving sheave, the diameter D is smaller. So the bending stress sigma 1 means there is larger than that of sigma B2. So the maximum stress occurs where the belt enters the small sheave. The bending stress is large, and the tensile stress on the tight side is large. So there is the maximum stress for the belt. And this finger represents the stress distribution and the maximum stress on the belt. And the maximum stress is the tensile stress sigma 1 plus the bending stress sigma B1 and plus the centrifugal stress sigma C. There. Okay. And this is the centrifugal stress, this is the tensile stress, and this is the bending stress. This is for the stress analysis. We consider all the stresses on the belt. But for force analysis, we just consider the tensile stress and to calculate the force transmitted by the belt. And the force acting on the X, the pulleys are mounted on the shaft, So the force acting on the axis means the force acting on the shaft, and we can calculate the force acting on the axis FQ. Use this to calculate. Okay. And the elastic grip and slippage of belts. Okay. We consider this. The belt first contact the driving pulley. First contact the driving pulley at which point? At point A1. Point A1. And with tight tension F1 at speed V. And for arc A1C1, there is no changes in tension F1 and speed V. For arc C1 B1, for this arc, the tension on a differential belt element close to the height side is greater than that close to the slack side because the tension on the tight side is larger than on the slack side. So, resulting in the elastic deformation, for the elastic deformation, the lambda 1 is larger than the lambda 2. Then the elastic grip begins. And for point B1, the belt leaves the driving pulley with slack tension F2 and a reduced speed. And for the driven pulley, the belt tension increase from F2 to F1, resulting a gradual increase in elastic deformation of belt along arc C2 B2, and belt speed is higher than linear speed of driving pulley. So this is the elastic grip or slippage occurs, and the relative slide between the belt and the pulleys due to different tension on tight and slack side is called elastic grip. And this is for the calculation equations of V1 and V1 and V2. V1 is this speed, and V2 is this speed. V2 is the linear speed of driven pulley. Okay, and then we know V1 and V2, and we can calculate the slip ratio epsilon is V1 minus V2 and divided by V1. And we also can calculate the speed ratio N1 over N2. N1 over N2 can use this to calculate the speed ratio is approximately equal to D2 over D1. And to prevent slippage, there should be a limitation on the maximum effective tension FEC. The maximum effective tension at critical slip stage can be expressed as this. And the maximum stress on the belt should less than the allowable stress. Then we can calculate the maximum effective tension, and then we can calculate the basic power rating for a single standard weight belt. Use this to calculate. And PR is actual power. The basic power P0 is obtained under specific test conditions, and the test condition specifies as a moderate length belt running on identical diameter sheaves, transmitting a steady load. And in practice, a given belt can carry a great power as the speed ratio increases. The increment of transmitted power is delta P0. The contact angle and belt length is different from the specific test condition, and the actual power acting on a single weight belt is as just as this. Is equal to P0 plus delta P0, and test K alpha and KL should less than the allowable power. P0 is the calculated basic power, and K alpha is correction factor for the contact angle. KL is correction factor for belt length. And this table lists the P0, the basic power, and this is the type of V belt, and this is the datum diameter DD1 for the driving pulley. And this is the speed for driving pulley. And then we know the value of speed and the types of belt and the diameter DD1. Then we can obtain the value of P0, the basic power rating on a single ordinary wave band from this table. And and for other diameter and speed not occur in the table, we can obtain the P0 by interpolation. And this is basic power P0 for narrow wave belt, and this is the types SPJ, SPA, SPB, and SPC, and this is for standard wave belt. Okay, and this is the length coefficient KL. If a belt length is different from the specific belt length, when the P0 is obtained, a belt length correction factor KL is introduced. It's illustrated in the table. And then the actual power is just 2. And this is the power increment delta P0, and a given belt can carry a greater power increases. The increment of transmitted power delta P0 is listed in this table, and it added to P0 is take this factor into account. And then first we should know the type of belt and the speed of driving pony and the speed ratio. And then we can obtain the power increment delta P0. And this is for delta P0 for narrow wave belt. And this is the K alpha contact angle coefficient K alpha according to contact angle of 180 degrees. The correct factor K alpha can be selected in this table, and the correction factor K alpha for other contact angles can be obtained by interpolation also. And then the determination of the type of number of ordinary wave belt. We have PCA, the calculated power is Ka times P. Ka is service factor or working condition coefficient. And determination of mode according to PCA and small belt pulley speed N1 determined by the selection diameter and the determination of number, the number of belt Z. Can use this to calculate. P is the calculated power. The allowable P0, we use the actual power P0 plus delta P0 and then times K alpha times KL to calculate the Z. And this is the table for working condition coefficient, and this is for the condition of working machine, and this is for the prime mover. We usually choose this condition, in this condition, and there is the working hours per day. And for example, for a light load conveyor, and it works 8 hours per day, 8 parts per day. Then we can choose the working condition coefficient Ka is 1. And if it works 12 hours per day, we can choose the working condition coefficient 1.1 there. And this is the selection diameter of standard weight belt, And then if we load the power and the speed of driving pony, then we can obtain a point, and law is coordinate. And the coordinates of points falls in different areas. This J, A, B, C, D, E means the type of the standard weight belt. And for example, if the point is located in there, means the power is larger than 20, and the speed is nearly 800 revolution per minute. Then this point located in area C. So we can choose a C-type standard weight belt, and the diameter of the pony D1 can vary from 100 to 350. Of course, the selection is not absolute. This is only a suggestion. This is only a suggestion. If the point located in this area, you also can choose a B-type belt. You also can choose a B-type weight belt, and you also can choose the diameter D1 less than 200, and then you should to check your design if acceptable or not. And from this diameter, we can choose the types and the diameter D1 for the driving pony, but it's not absolute. It's just a suggestion. Okay, this is also the selection diameter. And this is the selection diagram for narrow weight belt. We also calculate the power and lose the speed N1, and find the coordinate of the point, and choose the types and the DD1 for the narrow weight belt. And the key point of this chapter is design of belt drive, and the design procedures include: first, computer the design power PCA. PCA, we can calculate from this the KA times P. P is the power. Usually we give you this P, and KA can obtain the KA from this table. KA is working condition coefficient, KA, and we should know the condition of working machine and the working hours per day, and then choose a suitable KA. First, to calculate the design power PCA, and then specify suitable belt type according to the rotational speed of driving sieve N1 and design power PCA, and then from the selection diameter of standard weight belt, we load the PCA and the speed N1, and then we choose the type of the belt and the D1 for the driving pulley. And then determine the sieve size. The size of driving sieve should be greater than the minimum diameter recommended for each belt type from the selection diagram. And then the diameter is the diameters are standard. This is for A type, this is for B type, this is for C type, and and we should choose standard value for belt. For example, from this selection diameter, which for this point is located in the area C, we choose a C type, and the diameter should be larger than 200 and less than 315. Then from this table, you can find the table in your textbook. From this table, we can choose its type C, and the diameter should be larger than 200 and less than 350. Then we can choose 200, 212, 224, 236. Choose these values at the pulley, at the driving pulley. All the diameter should be standard. Okay, all the diameter should be standard. The size of driving sieve should be greater than the minimal diameter. And then we choose a driving sieve diameter, and then we should calculate the driven sieve diameter, D2. How to calculate D2? How to calculate D2? And from there, if we know D1, we can use the speed ratio to calculate D2. So we should know the speed ratio of the belt drive. And then we choose a diameter of driving pony, and through speed ratio we can calculate the driven sieve diameter. We should notice that the diameter of driven sieve or driven pulley is also standard. You can choose from this table, and then we should check our selection. So we should specify that the belt speed should be within a range of 5 to 25 meter per second, and then check the error of speed ratio. The delta I is the absolution of the d2 over d1 minus I and divided by I. I is the speed ratio, and the error of speed ratio should less than 5% to check our selections of the sieve size. And then comfort the center distance and the belt length LD. First, we should specify a trail center distance A0. So the choice of A0 is critical. If the A0 is too small, it will increase the frequency and increase the likelihood of vertical failure. And this A0 is limited by sieve dimensions and minimum contact angle. And if it's too large, it will increase the size of the belt drive, will cause vibration, and so it's limited by a variable belt determined length. So they choose how to choose trail central distance A0. We use this equation. It should larger than 0.7 times d1 plus d2 and less than 2 times d1 plus d2. d1 and d2 and the sieve diameter for driving and driving pulleys. Use this to choose A0. And then if we know A0, we can compute the preliminary belt length LD prime. We use this. We have learned that we use this to calculate LD prime. And we choose A0 and choose the D1 and D2. We can calculate LD prime. And then select belt determined length LD because the belt length LD is standard too. Also from this table, and this is for datum diameter, and there is for the standard V belt datum length LD for A, B, C type, and then we can find a standard value of LD, which is near the or close to the computed length LD prime. And then we should compute the actual center distance A. Use this to modify the actual distance A. It's the selected traverse center diameter A plus LD minus LD prime, then divided by 2. Use this equation to calculate the actual center distance A. And this is the minimum A, and this is the maximum A. And then we should, and for this we should computer contact angle on the smaller sieve or on the driving sieve alpha 1. And we should satisfy that the contact angle of alpha 1 should be greater than 120 degrees to ensure adequate contact and frictional force. And that is the contact angle on the small sieves alpha 1 must satisfy. We use this to calculate alpha 1. Do you remember? It's pi minus this, and should larger than 120 degrees. A is the center distance. D2 and D1 is the diameter for driving and driving sieves. And this use this equation, we can check the selection of center distance if can acceptable or not. And then compute the number of belts required to carry the design power. And if a single wheel belt has insufficient capacity, multi-belt may be used. The number of belts required is calculated from this. So PCA, we can obtain PCA from this equation, the KA times P. P is low, and the KA we can obtain from the table. And the PR is P0 plus delta P0 and times K alpha times KL. We also can obtain P0, delta P0, K alpha and KL from tables. And the number of belts should less than 10. And then decide initial tension F0. Initial tension F0, we use this equation. You just need to remember the equation and use this to calculate the initial tension F0, and they compute the force acting on the shaft FQ. Use this to calculate FQ. And for the sieves, these are sieve structures of wheel belt drives. The sieve structure include solid sieves and thin web sieves and hollow plate sieves and spoke sieves. And for the solid sieves, it's under the condition the datum diameter is less than 2.5 to 3 times the diameter of the shaft, and the sieves is mounted on, so it's suitable for small diameter sieves. And this is the solid sieve. And for thin web sieve, and this is for the whole and this is for the whole plate sieve. Both of them are suitable under the condition The datum diameter are less than 300 millimeter. If the calculated diameter is less than 300 millimeter, we can choose thin web sieve or whole plate sieve. And for the spoke sieves, the datum diameter is more than 300 millimeter. Like this is the spoke sieve. So we choose the sieve structure according to the diameter. If the diameter is small, we choose solid sieve. And if the diameter is less than 300, we choose seamed web or whole plate sieve. If the datum diameter is more than 300, we choose spoke sieve. And this is the size, the size for ordinary weight-belt sieves. It's standard. And now let's have a break. Okay, let's have a break
Okay, Lord.
for 20 minutes. Okay, have a break. Okay, let's continue. The design procedure of belt drives is very important. First, computer the design power PCA, and in order to calculate PCA, we should choose KA. KA can be choose from the table, and then simplify suitable belt types from the selection diagram of standard V belt and narrow V belt, and then according to the KPCA and the driving shift speed N1 to select the belt type, and determine the shift size from the selection diameter. We have range. We can obtain a range for driving pulley diameter, and then we select a standard value from that table for driving pulleys or shifts, and then we use the relationship between diameter of driving pulley and driven pulley and the speed ratio to calculate the value of diagram of driven pulley and choose a standard value. And then we check the selection. Then we should certify that the belt speed should within this range from 5 to 25 meters per second. And then check the error of speed ratio delta I. Delta I use this equation, and we should certify that the delta I should less than 5%. And then confirm center distance and belt length. First, we choose a center distance alpha O, and how to choose alpha 0? We use this from within this range. Within this range, choose the trial center distance alpha 0. And according to alpha 0, we compute the preliminary belt length LD prime, and then select standard belt length LD, and then modify the center distance A. Use this to obtain the actual center distance A, and then compute the contact angle on driving pulley or driving shifts alpha 1, and we should satisfy that alpha 1 should larger than 120 degrees. We also use this to check the selection of center distance A, and then compute the number of belt required. Use this equation, and PCA is obtained from there, and P0 delta P0 K alpha KL can obtained from tables, and then to decide initial tension F0 and compute the force acting on the shaft, and also choose the structure of shafts according to their diameter. So let's see the example. We should need to design a V belt drive for a conveyor to be driven by power. The power is 7.5, and we lost the running speed. Running speed is 1,450 revolutions per minute, and the belt drive has a speed ratio, so we lost the speed ratio I is 3.5, and works less than 12 hours daily. And select type A belt, and the mass per unit length of type A belt is Q. We lose the mass per unit minute Q, and then to design a V belt drive. So it's then should design a V belt, and according to the design procedure. And first, we compute design power PCA. And how to compute PCA? How to compute PCA? And you can obtain the design process on page 136 in your textbook. And who can tell me how to compute PCA? Who can tell me how to compute?
Now she will use the formula.
Oh, you use the formula. Yes, use this. PCA, Ka times P. We lost P is 7.5. Okay. And then we should load the Ka. Okay. And for a conveyor, and there conveyor, and the working hours per day is 12. Okay, it's 12. So it's within this range. So we choose Ka is 1.1. Okay. So the Ka is 1.1. And then the PCA is 1.1 times the power. So the calculated PCA is 8.25. And then determine the diameter and the type. The type has selected A type. Okay. So determine the diameter of shafts. In your textbook, it choose the diameter of driving shaft D1 is 100 millimeter, and from our selection diagram, the calculated power PCA is 8.25, and the speed is 1,400 there. From this diagram, we can choose B type, but in the example, it choose A type. It choose A type diagram. So this diameter is just as a suggestion. You also can choose other types. And in our example, it choose A type, and then it choose a diameter D is 100 millimeters, so it's standard diameter. according to table 6.1. And then select sleep ratio epsilon. Select the sleep ratio, and then calculate D2. We also the speed ratio is approximately equal to D2 over D1. So we also can use this to calculate D1, but there we consider the sleep ratio and select as sleep ratio, and the calculated value for D2 is 344.8 millimeter. Is not standard, okay? So we should choose standard value from tables, and then select the standard value as 355 millimeter according to table 6.1, and then check the speed. The speed V is pi times diameter times speed, and divided by 6 times 1000, and then this speed should within the range from 5 to 25 meter per second. So check this speed of the belt is acceptable, means the selection of D is acceptable. And then check the error of speed ratio delta I. The delta I should less than 5%, and then it's acceptable. So the speed error of speed ratio acceptable. So the selection of D1 and D2 is acceptable, and then confirm certain distance. Specify a trial center distance alpha 0. We use this to select the alpha 0 should within this range, and we lose D1, and we select D2, and within this range we select alpha 0 is 500 millimeter, and then calculate the LD prime, the preliminary belt length LD prime. Use this, the calculated LD prime is 1747 millimeter, is not standard, so we should choose a standard value. And from table 6.1, we choose a standard value 1750 millimeter, and this is for the standard belt length. And then A belt, we choose this for A belt, the standard value, we choose this, and then we modify the center distance. Use this to calculate the center distance. It's 502 millimeter, and also we can calculate the minimum center distance and the maximum center distance. It can change within this range, and then compute the contact angle on driving sheave. Use this. We lose calculate the center distance is 502 millimeter, and we select D2 is 355, and D1 is 100, and then calculate the alpha 1 contact angle for driving sheave. It's larger than 120 degrees, so it's acceptable. So the selector is acceptable, and then compute the number of belts required. We use this. So we should choose P0, delta P0, K alpha, and K L. And in this example, we lost the speed, and D1 and I, and we can from the table choose P0, delta P0, and select K alpha and KL, and then calculate the J is 6.02. So we select the number of belts required is 7, and then convert the initial tension. We load the Q and calculate the V and Z and calculate PCA and loss K alpha and calculate the initial tension F0 is 139 and then compute the force acting on the shaft and choose structure for sheaves. We know that for driving pulley, the diameter is 100, and for driven pulley, the diameter is 355. So we can choose a solid sheave for driven sheave because the diameter is smaller. And for this, diameter is larger than 300 millimeters, so we can choose spoken sheave for driven sheave. Okay, for this example, any question? Any questions for this example? Any question? Okay, if not, we'll proceed to the example 2. Example 2 is to design a wheel belt drive for a belt conveyor to be driven by a power of 4 and the speed and below the speed and1 is 1440 revolutions per minute, and then the belt drive has a speed ratio I is 3.4 and works less than 10 hours daily, and we lose the Q, the mass per unit. No, not select type A, not select type A. There is equal. There is a okay. So, for the we lost the design procedure from 1 to 8 to computer design power, determine diameters of shapes, and conform certain distance and belt length, compute contact angle, and compute number of belts, and confine initial tension F0, compute the force acting on the sheave shaft FQ, and then do the structure design for the sheaves. So, you have 10 minutes to do to calculate or design by yourself, okay? 10 minutes, okay? Okay. You have 10 minutes to design by yourself for this example, okay? Anyone? Anyone? Okay? Is anyone here?
Okay, Laushi, we are trying.
Okay.
Yeah.
I will send this PPT to the group, okay? Send the PPT to the group. You design by yourself first. Okay?
Okay, Roshi.
Okay. Wait a minute. I send the oh sorry, I can't find the group there. The belt by
তন্দুর রুটি ধান দল্লাই
So have you finished? Have you finished it, the design?
Laushi, I couldn't solve it. Could you please solve for us?
Okay. Okay, let's say the solution, okay?
Okay, Laushi.
And this is the 128 is the design procedure. And first, computer design power PCA. And we know that P is 4 and speed of pulley of the driving pulley N1 and lost the speed ratio I and and it works 8 hours daily, okay? This
Yes.
what we have learned. And then first compute design power PCA, then we should select KA, okay? Because PCA is KA times P. So choose the KA. KA is a belt conveyor, okay? It's a belt conveyor, and it works 8 hours daily. So the working hours per day is less than 10. Less than 10, okay? So we choose 1.1, okay? Choose the 1.1. So KA is 1.1. Then we calculate the PCA is 4.4, okay? And then we determine the diameters of the shifts. And then we lose the speed to N1 and we lose PCA. And then from the selection diagram, the calculate power PCA is 4.4, okay? It's 4.4, and the speed N1 is 1,440 revolutions per minute, okay? So the on the horizontal axis, PCA is 4.4, okay? And then the speed N1 is 1,440. So the point will locate there, okay? Locate in this area, okay? Any question? Okay. This is the speed and this is the PCA, so we can find the point. The point is located in area A, so we can choose A type belt, right? We can choose A type, okay? And then the diameter D1, the diameter for driving pulley can within this range from 80 to 100. Okay. So the driving pulley, the diameter D1 can within this range. And then from this table, we should choose a standard value for belt type. For belt type A, should larger than 80 and less than 100. So we can choose 85, 90, 95 as the driving pulley diameter D1. Any question? Any question? We can choose 85, 19, and 95 as the diameter D1. And in there, we select D1 is 90 millimeter. According to the table, we choose the standard value, okay? And then calculate D2. D2 is the diameter for the driven pulley. We use this D2 is approximately equals to speed ratio times D1. And we know speed ratio I is 3.4. And we select D1 is 90 degree, and then calculate D2 is 306 millimeter, and this is for the calculated value. And and for D2, we should choose standard value. We choose which? We choose which standard value for D2? Tell me.
Uh, 315.
Yes, we can choose this. We can choose this standard value for D2, okay? And then select the D2, it's 350 millimeter according to the table. And then we should check the selection. How to check the selection? The belt speed should within a range of 5 to 25 meter per second. And then we calculate the V, the linear speed, and use this is pi times D1 times N1 divided by this. And the calculated value is 6.78 and is within this range, right? Within this range. So then the selection is acceptable. So we choose D1 is 19 millimeter and D2 is 350 millimeter. Okay, and then we should calculate the central distance A, and A should within this range, okay? Should larger than 0.7 times D1 plus D2 and less than 2 times D1 plus D2. And D1 is 19 and D2 is 350. So the A0 should larger than 283.5 and less than 810. And then we select A0 is 500 millimeter. You also can choose 600 or 500 or 550 millimeter. You can choose the value within this range, okay? And then we calculate LD prime, okay? LD prime, how to calculate LD prime? We use this, okay? We lose A0 and D1 and D1 and D2. And then we calculate the LD prime is 1659.2 millimeter is not standard value. Then we should choose a standard value for belt length. So we choose which one? We choose which one? Choose a standard value for belt length from this table. So we choose which one? Tell me. We choose which one? Can you tell me? Can you tell me? Choose which value for the belt length. We know that it's a type weight belt, and the standard value there. So we should choose a value close to the calculated value. So we choose this.
1640.
Yes, we choose this. Yes, we choose this as the standard value. So we modify the central distance, and we can obtain A. Use this to calculate. A0 is we choose before is 500, and this is the standard value, and this is the calculation. The calculated value, and then we calculate the actual center distance A is 490 millimeter. Okay, and then below that we calculate PCA and select D1 and D2 and select LD and calculate the center distance A. And then we should check the selection. How to check? To compute the contact angle on driven sheave. Use this equation to calculate the contact angle alpha 1 and D2 and D1, and the center distance is both are low, and then calculate the alpha 1 is larger than 120 degrees, so the selection is acceptable. Okay, selection is acceptable, and then we will say this, and then compute the number of belts. How to compute the number of belts? We use this equation. We use this equation to calculate, okay? To calculate, and then, and first, and oh, let me see. Sorry, there is a little wrong. There is not A, not A. Oh, I can't modify this. So there is lot A. And then we lost the PCA is 4.4. So we should choose the value of P0. And this is the table for the standard P0. And this is A type weight belt, okay? A type. And the diameter D1, we select D1 is 90, okay? Is 90. And then we choose a value when the speed N1 is 1,440. So there is can't find 1,440, but we know the P1 under 1,200 and 1,450. So we can obtain the value of P0 by interpolation. By interpolation. Okay?
Yes.
We can by interpolation and then it should within this, it should larger than 0.93 and smaller than 1.07, okay? Within this range. And then we use interpolation to calculate the P0. P0 is within this range, And we load the P0 under this speed and P0 under this range. And then we calculate the P0 when the speed is 4,040. And we calculate P1 is 1.064. This is the calculated P0 from the table by interpolation. So, any question? Any question for this? So, do you know how to use interpolation to calculate P0? How to use interpolation to calculate P0? Any question? So, all of you know how to use this, okay? And then we choose the P0. And second, we should choose delta P0, okay? And also from the table, A type, and this is for speed and 1, and this is for speed ratio, and the speed ratio I is 3.4, is larger than 2. So we should choose the value within this range, okay? And there is no values for N1 is 1,414, and we also can calculate the delta P0 by interpolation, and the value is 0.17. Okay, the point is 0.17. It can calculate the delta P0. So we load P0 and delta P0 and then choose K alpha and KL. There is no A. And then for the contact angle coefficient K alpha, and this is the alpha 1. In this example, we calculate alpha 1 is 153.7 degree. So the K alpha is in this range, and we also use interpolation to calculate the K alpha is 0.925. Okay, this is for the K alpha, and then we should know the KL, and this is for the KL, and this is the length, for the belt, and this is the type. We choose A type. Okay, and the length is near this. So For A type, we choose the KL is 0.99. And then we load the 4 parameters. And then we calculate Z, use this, and it's 3.89. So we select Z is 4. Select the number of belt is 4. Okay. And we know the Q and the V. V is calculated before in where to check the selection. To check the selection of selection of diameter. Selection we have calculated the V. Okay, we should within the range from 5 to 25, and then and then we load the Z and the V, and we load the Q and PCA. We calculate the initial tension F0 is 143. And then compute shaft force FQ. Use this. J is 4. And the calculate the F0 is 143. And the alpha 1 is this, and then we calculate the FQ, the shaft force, and then design the belt sheaves. D1 is 19 millimeter, D2 is 350 millimeter. So from this, we select solid sheaves for driving sheave and spoke sheave for driven sheave. Okay, this is for the design procedure. And for belt drive, the design procedure is very important, and there are a lot of parameters we needed can be obtained from tables. The Ka, the P0, and delta P0, K alpha, KL. And then according to calculation equations to obtain a larger parameters for the design. So for the design procedure, do you have any question?
No, 老师。
Okay, all of you have mastered the design procedure. Okay, it's great. And then let's proceed to the next part. And then for the grooved idler, when the center distance of a belt drive is fixed, a groove idler is used on the inside of slack strand close to the large sheave to take up slack. Like this. It's on the slack side, and close to the large sheave. If the center distance is adjustable, belt tension can be maintained by regular manual tension or by the weight of rotated or hug motor, and like this, and why we choose the slack side and near the large shelf to install the grooved idler, because for the side 3, 4, 7, 8, it's on the tight side. All right, it's on the tight side. If we install grooved idler on the tighter side, inside 3, 4, 7, 8, it will increase the tensile force because the tensile force on the tight side is larger than that on the slack side. So it would decrease the strength of the belt. And for the slack side, if we install the grooved idler on side 5 and 6 on the outer side, like this, so it will increase the bending and cause fluctuating stress. So we should install the grooved idler on the inside of the slack side. And for the for the side 1, it's near the smaller shaft or near the driving shaft in this side. On the driving pulley side, it will decrease the contact angle alpha 1. Okay, it will decrease the contact angle alpha 1. We know that alpha 1 should larger than 120 degrees. Okay, so if we install grooved idler on this side, it will decrease the contact angle. So we install grooved idler in 2 sides. In there. It's on the inside of slack trend close to the large shaft. And there on the inside of slack strand close to the large shaft. So for these pictures, which one, A, B, C, D, E, F, G, H, which one is correct to install the grooved idler? Which one is correct? So which one is correct? Which one is correct? Anybody knows? Which one is correct?
B 老师
Yes, B is correct because it's installed on the inside. Okay, on the inside, and should near the larger shaft. Should near the larger shaft. And for A and B, the difference is for A, the rotate direction is clockwise. So the bottom straight is tight side, okay? And for B, the bottom street is lakeside, so it's on the inside of the lakeside near the large shave. So B is correct. So this is all for today's lesson, and we should focus on the design procedure of the belt, and the design procedure is very is very important. And we also know the yeah, any question?
Yeah, I have a question. Page number 69.
Number 69.
Yes.
69. Let me see. Oh, it means there?
Yeah, in the V. This
Oh, the,
60 times 1,000.
oh, the way to
Six.
check. You
Yeah,
mean
this
the
number times 1,000.
numbers, the way 6
Yes.
there times this? You mean this?
Yes. Yes. Yes.
Okay, okay, I see. Let me see. Okay, for this, the D, you mean the D, we choose D is 90 millimeter, okay?
Yes.
D is millimeter, so for the V is meter. So we should change millimeter to meter, so it should divided by 1,000. Okay?
Okay.
And for the speed N1 is revolutions per minute, and for V is second. So we should transform minute to second. Okay?
Okay. Okay.
So we so divided by 60. Okay?
Okay.
Okay. So any questions? So, and you should master the types of belt, and to master the force analysis and the strength analysis of the belt, and you should focus on the design of belt drives, and you should know how to select the parameters value from tables, and how to check your selection, and this is all for this class. Okay, so class is over. Okay, see you next time.
She see you next
Thank you.
Okay, bye bye.
Bye bye, Laushi.